Hello, all. So, I'm going to talk to you about something that I know that you have learned about before, probably in physical science, also in elementary school. But, like physics always is, we're going to be looking at a particular topic and then going into a little bit more detail, specifically with some math. So, let's start with the basics. What I'm talking to you about today is refraction. And by definition, refraction is the bending of light because of a change in speed. So in the previous unit, as well as I know in the intro stuff that you did with Miss Hart, we talked about before that the only way to change the speed of any wave, which includes light, is to change the medium. So for refraction, what we're going to be looking at is how light changes its behavior, how it bends in different directions because of changing its medium, going from one particular material to another. So some pictures, because it's always nice to look at some pictures, right? I actually got this picture from one of my students a few years ago, and it was taken obviously in the woods. It was for an art project. And she was like, "Hey, I got this amazing picture. Do you want it?" And I went, "Yes." So the reason why I like this picture so much is because it definitely emphasizes this whole idea that light travels in a straight line. So you can see these beautiful lines, rays of light, like we like to call them, right? And this is all in the same medium of air. Now, what happens if we were to go from air into water? This is the classic example that I know you've seen in terms of refraction, where you've got this whole air in the top here with our straw, and as it goes into the water, right here in that middle area, you can see that change. You can see that bend and what we normally think of as that break that happens. This is a picture from the zoo. This is in the reptile house. It was actually the last time that we went before all this craziness with COVID happened. And what I always tell my students is I'm always a physics teacher. So anytime like I'm out and about with family or whatever, and I see something that I'm like, oh my gosh, I have to use this, I always take pictures or videos or something like that. And so in the reptile house, of course, there's lots of turtles. And you can see right here that obviously, here's the water line, right? And so you can see that when the light goes from air into the water, it has a bend, it changes. This is the same turtle. It's just when we look at it from above, we can see the whole body. But then when we look at it from below, then we only see the bottom part. So if I get rid of that line here, what you're going to see is you see this bend, this change in vision because of that change in speed. So here's another example. This is actually one of my favorite, I guess, habitats in the reptile house, which is the little teeny itty bitty turtles. They are just so precious. But these are the same two turtles again. So depending on what direction you're looking at, from above in the water, you see two turtles. And then from below, you only see like 1.5 turtles. And that's because that light is going from the air into the water, and that bending that's happening because of that change in speed is changing your perspective that you see. So here's another example of one of the little teeny guys. And again, that's one turtle in that top corner. And this is a video that I took, which I think is also very, very cool. And so whenever you change your perspective, so you see the same two turtles, see they disappear and then they reappear. And it's all because of that bending of light that happens because of a change in speed. So what we're going to do now is we're going to look at why. So why did the straw break whenever we saw it in the water? Why did the turtles disappear? Why did the turtles become double and things like that whenever we're going from one medium to another? So in this demo, see I've got 2 straight pins and they're perfectly lined up on this beautiful pink line. And imagine that, there is this beautiful pink outline that perfectly fits my little prism right here. So what we're going to do is we're going to look at this line. Instead of from air, we're going to look at it through the prism. And so what I want to do is line this up so those pins are perfectly in line. So you see down here at the bottom, they are in line. Then I'm going to take my 2 new pins and I'm going to position them so that they are also in line. One here. And one here. So as you can see from here, they look like there are 4 pins in a perfect line. Now, from above, do they still look like they're in a perfect line? Yeah, they do. Let's check. So if I take a ruler and put it along these 2 dots, are all 4 of them going to be in a line together? And lo and behold, check it out. They are. We have 4 pins that are perfectly in line with each other. Well, that doesn't explain why the turtle was cut in half or disappeared. All right. Oh, we weren't looking directly down into the water. So what we're going to do now is we're going to look at 2 different angles. So now we're looking at a small angle into the water, here a prism, and then a larger angle into the water. So instead of straight down, because we're going to be doing everything from straight down, we're going to draw this out in just a second to explain a little bit better. But nonetheless, now let's see what happens if we are not going straight down into the water. So I'm moving my pins where they are now in line again, perfectly on my pink line here. Put my prism, and now here we go. Let's look through the prism. All right, let's see. Don't look at my mess in the background. All right, here we go. Ready? Let me put my next 2 pins here where they are also in line. There's 1 and 2. All right. So if I look at it from this perspective right here, we can see that the blue are now a little bit off from my pink. What happens if I take this prism away? Well, let's line up again with our original pins. And what we should see now is, look, the pink pins are not in line with it anymore. There's a deflection. So actually, I'm going to draw this in. Oh, actually, I can't do that because I'm holding onto my phone. But anyway, all right, what if I put it on this side? See, you can see this tiny deflection right here, right? It is not in line with that pink line. All right, So let's predict. What do you think is going to happen if now it's a much bigger angle? So now I'm going to put my blue pins here along a larger deflection from straight up and down, right? So what do you predict is going to happen? Let's find out. Okay, here we go. Let's see what happens here. I'm gonna put this one, let's see, make sure it's in line. There we go. And let's see, there we go. There we go. Hey, check it out. Look at my blue pins. You can actually see the deflection now, can't you? So if I get these in line, like so, if you look at the blue, you can see that there's a much larger deflection. So much, in fact, that it's pretty darn obvious that these are not in line. Well, what if we take this out? Let's put our ruler. And looky there. Much bigger deflection. Now, one thing to note, in the previous one, this was also the case. Notice they are parallel to each other though, right? And this is why whenever that picture I showed you of the water cup, that straw looked broken, but it didn't look bent. It just looked broken. So here you can see the line breaks. So why does this happen, right? That's the big question. So now we can see that indeed, when we go from one material to another, it's going to break. All right, here's the best way I can think of to explain why this happens. So here is my little scenario. Look, there's road and there's gravel. So I have borrowed my little gator here from my youngest son. And so where is this gator going to be able to drive faster? Well, obviously on the road. So whenever the gator goes perfectly in line onto the gravel here, it's going to slow down and go slower. But see, since it hits perfectly straight on, it's going to slow down at exactly the same rate on both sides of my little gator. Now, what if we were to hit at an angle like this? At an angle, notice this wheel hits first, which means it slows down while this one is still moving. And so what it's going to do is it's going to twist. And it's that twist that causes that bending of light. Now, the larger the angle is here, then the more it's going to bend. And that's what we saw in this example. So in this one, so straight down, here we go. Let's write some stuff, right? Equals straight down again. Here, there's just a small deflection from that straight down. So small angle or deflection equals small break. So that was where we saw that parallel line, right? There was a small deflection right there. And then over here, we've got a large angle. So a large angle from that straight down is going to equal a larger break. Well, there's a trend, right? So why am I caring about this whole straight down thing? It's because we always measure these angles from something called the normal. And so I'm just going to kind of sketch it in here. The normal is this straight down line. The normal is always going to be perpendicular to the surface. We normally go straight down. Now, you might remember the normal from first semester whenever we were doing these things. So we'd have FG going this way and going up, we'd have F norm. Well, that was the normal, and that's because this was our ground. And so again, it was at a right angle, so perpendicular to the surface. So here it's again perpendicular to the surface. So see, small angle. This one has a large angle from the normal. All right, so now let's go back to our road and gravel situation. So straight down means that it will have no deflection. Larger angle means more deflection. And so we talk about this as bending towards the normal and away from the normal. And so if I were to sketch my normal line right here, we would have a bend towards the normal. And the reason why this happens is because in the gravel, it goes slower. So, slower medium equals smaller angle equals bend towards normal. All right, well, let's do another scenario. Now we got the road and grass. Grass, if you were to, imagine this vehicle, right? So my little gator again. Compared to the road going into grass, it's going to be even slower. And so we've got our normal line going here, and we have our angle here. Then this one is going to deflect towards the normal even more. So even slower means an even smaller even smaller angle, which means it bends towards the normal more. All right, well, what if we were to do the opposite, right? So what if we were to start in the grass and go up into the road? In this situation, we would be going from a slower to a faster. And so if we were to have an angle like this, then we would have that first tire hit and speed up, which would deflect it away from the normal. So if we were to instead start in a slower material, like this, imagine that's a straight line, then it would deflect even further away. And all of this is because of a change in speed. Now, we know exactly how much these things are going to deflect based on the material. So now instead of gators, let's go back to light. So light is fastest in a vacuum. Slowest in a solid. So what this means is that as we go from a vacuum into, say, a gas, we're going to see a little teeny deflection. If we go from the vacuum into a solid, we're going to see a very large deflection. And so we know exactly how much that's going to be depending on the material itself. The way we know is something called the index of refraction. The index of refraction tells us how much it slows, how much light slows, or how much faster a vacuum is compared to a medium. Since it's how much more, or how much faster, how much slower, this is a ratio. It's just going to be a number. It's going to be like 5 times or 2 times or something like that. And so I'm just going to go ahead and give you the equation. Like so. NS is the index of refraction. So N is the index. This tells us how much faster it is in a vacuum, or how much it will slow, or how much it will bend. C, you learned about from Ms. Hart. C is the speed of light. In a vacuum. This is where it's the fastest, right? And we always know that number. That number is always 3 times 10 to the 8 meters per second. Vs is going to be the speed in a substance. So the S stands for the substance. So whatever substance we're looking at, this S stands for that substance. So if we're looking at, say, water, then it'll be the N of water is the speed in water, N of the prism, V of the prism. So let's just do an example. How about that? All right, well, we've got NS equals C over VS. We always know C. C is a constant, 3 times 10 to the 8. This substance has this speed, and so that's going to be this one. So we have NS equals 3 times 10 to the 8 meters per second over 1.5 times 10 to the 8 meters per second. And so if we were to do the math here, we would get 2. Now notice I made sure I put the units in here because we have meters per second divided by meters per second, which means that they cancel out. So the index has no unit. Now, what does this number mean? An index of 2 means that light is 2 times faster in a vacuum than in this substance. That's what it means. Now, we could say, instead of saying 2 times faster, we could say it's twice as fast. Now, this is just a random one, right? Why don't we do a for realsies? So, how about, let's do the prism. All right, well, this one's a little bit tougher. Let's see, we got NS equals C over VS. This time, we have the index dex. So we have 1.58 equals that 3 times 10 to the 8 over VS. Well, we're having to solve for the bottom of a fraction. So here's what we can do. There are two real methods I can think of to do this. So method number one is what I call the algebra method. In the algebra method, we will take 1.58, 3 times 10 to the 8 over VS, and we will multiply by VS. The reason why we want to do that is we've got to get rid of the fraction. Step one. So 1.58 times VS is now 3 times 10 to the 8. And then to get VS, we divide both sides by 1.58. And so, let's see, that gives me a VS of, rounding, 1.9 times 10 to the 8th meters per second. The other way that I can think of is the cross multiply method. And so we'll go back to this 1.58. We'll go back to the original here. Well, 1.58 is the same as 1.58 over 1. And so from here, we can cross multiply. And lo and behold, we get the exact same thing in this step over here. 1.58 times VS equals 3 times 10 to the 8. So whichever method makes more sense to you, use that one. But nonetheless, in both of these methods, you get the exact same answer, which is 1.9 times 10 to the 8 meters per second. Now, interesting question. This one has an index of 1.58. This one had an index of 2. So a good question would be, which one has a slower speed? Well, we could compare the actual speeds themselves, right? 1.5 times 10 to the 8 versus 1.9. So this one is slower. So we could do a couple more trends here, right? So larger N equals slower VS. And that's because it's that many times faster in a vacuum compared to that substance. So we could imagine, let's say N of a vacuum is going to be exactly 1. 0, 0, 0, 0, 0, because it's 3 times 10 to the 8 divided by 3 times 10 to the 8. N of air. Well, air is a gas. Gases have very few particles, which means that it's not going to slow light down very, very much. And so air has an index of 1.0003, which is basically 1. So for the intents and purposes of this unit, when it asks you for the index of air, you're going to use 1 because air is pretty darn close to a vacuum. In contrast, N of water is 1.33. Water being a liquid means it's going to be even slower than an air, and so we're going to have a higher index. And then, of course, we had the N of the prism, which was that 1.58. So, gas, liquid, solid. You can see the index increases as we get into denser materials, and that's because larger index indicates slower speed. Now, one thing to also note about all these numbers, all are greater than 1. And that's because with that ratio, right? So N equals C over VS. VS is always going to be smaller than C. C is the fastest that light can go. C is the speed of light in a vacuum. So this is always going to be smaller, therefore this will always be greater than 1. All right, I think that's enough, right? That's a lot of material. So what we want to do now is try some practice.